We want to find all positive integers a and b such that a factorial plus b and b factorial plus a are powers of 5. Okay, let's dive right in with a solution. This is very symmetrical. A factorial plus b and b factorial plus a. They're the exact same expressions, but with a and b swapped round, which tells me that I can just assume, without loss of generality, that one of them is bigger than the other. So without loss of generality, a is less than or equal to b, and any solution I get like this, I can just swap a and b around at the end. Okay, cool. So we're assuming a is less than or equal to b. Let's play around with this. Can we find any solutions to this? Well, maybe if we look, well, let's try, 1 and 4 works. If I make a 1 and b 4, 1 factorial plus 4 is 1 plus 4, which is 5. And 4 factorial plus 1 is 24 plus 1, and that's 25. And 5 and 25 are both powers of 5. Great, that works. And so at the end, we'll also get a is 4 and b is 1 works, so swapping those around. What about any others? And we can think about this and play around with it. And eventually you'd find 5 and 5 work. So a equals 5, b equals 5. You'll get 5 factorial plus 5 in both cases, which is 120 plus 5, 125, which is 5 to the power of 3. Cool. Then you can play about it with it some more, and then you realize that the factorials get really, really big. So 6 factorial is 720, 7 factorial is 5040, and I don't really know my powers of 5 going into the 10,000s. So how can we deal with this for large values of a and b? We're going to make the critical observation that factorials are eventually going to be multiples of 5. In fact, it doesn't take too long. If a and b are at least 5, then these numbers here are going to be well, they're going to have a 5 in their product. And so therefore, this would be a multiple of 5. Okay, so for the time being, what we're going to do is assume that a is at least 5. So we're going to assume that a is at least 5. And so therefore b is at least 5. And now you can check that, well, we'll come back to this statement later, but we're going to assume for now a is at least 5. And then afterwards we'll look at what happens with a is less than 5, but in basic solutions. Anyway, what happens when a is at least 5? We can say that a factorial and b factorial are multiples of 5. Now, if we want these numbers here to be powers of 5, well, they must certainly therefore be multiples of 5 at the bare minimum. So if we look at, let's say, a factorial plus b, this whole thing has to be a multiple of 5. But we know that a, since it's at least 5, a factorial will be a multiple of 5. And so therefore, this guy here must be a multiple of 5. Okay, cool. So b is a multiple of 5. And with the exact same argument, but with this term, we get that a is a multiple of 5. So a and b are multiples of 5. Okay, cool. Now, what can we do with this? We can make a further observation if we look at b factorial plus a. So b factorial plus a is clearly going to be a multiple of a because b is bigger than a. So b factorial will contain an a in it, and obviously a is a multiple of a. So this guy here is very clearly a multiple of a. What does this tell me about a? This tells me that a must be a power of 5. So since this thing here is supposed to be, 5 to the power of something, this tells me that a is 5 to the power of something. Why is this? Well, let's say a wasn't a power of 5. If a wasn't a power of 5, it would have some other prime factor in it. Let's just say 3. So let's imagine a was a multiple of 3. But then this guy here is a multiple of 3. This guy here would also therefore be a multiple of 3. But then that would mean that a power of 5 is a multiple of 3, and that's impossible. A power of 5, the only prime factor in that is 5. So therefore, a cannot have any other prime factors other than 5, and thus must itself be a power of 5. Cool, so a is 5 to the power of something. Cool. What about b? Well, we're going to see here that b kind of hits a dead end if b is bigger than 10, or in fact, at least 10. So if b is at least 10, what goes wrong? Well, let's have a look at b factorial plus a. Well, we know that a is a power of 5, so this is going to be b factorial plus some power of 5, which is what a is. And well, again, we know that this thing here is a multiple of A or multiple of 5 to the K, so I can kind of factor that out. So this is going to be like that. Now, what's the issue with this? Well, we want this guy here to be a power of 5. And so in particular, it has to be a multiple of 5. Okay, this guy's not really doing anything. That's just a multiple of 5. But what about this thing here? Well, if B is at least 10, well, then that means that there's at least two multiples of 5 in B factorial. 5, 10, and if B is any bigger, then maybe other multiples of 5 as well. Now, we've only divided by A, which is one multiple of 5. And so therefore, this guy here, this number still has at least one 5 in it. And so this is going to be a multiple of 5. So this thing in the rectangle is a multiple of 5. And if I add 1 to it, that's not a multiple of 5. And this is a big contradiction because this number is B factorial plus A, which has to be a multiple of 5. So that can't occur. So that tells us B can't be at least 10. But B has to be a multiple of 5. And so therefore, since A is also at least 5, we get this. And that just means A equals B equals 5, which we already verified was a solution. So what have we worked out? We worked out that the only solution where A is at least 5 is the case where A and B are both 5. And so that means we only need to check the cases A is 1 through 4, and you can just check them by hand. So if you look at A, and again, actually, we can make our life a bit easier. So we only need to check A is 1 through 4. But even in this setting, because none of these numbers here are a multiple of 5, if we look at B factorial plus A, if B is any other number bigger than 5, or bigger than or equal to 5, this guy will be a multiple of 5, but adding on A will cause it not to be a multiple of 5. And so therefore, B must also be between 1 and 4. And now you just have, I guess, 16 cases, in fact, less than 16, 8 cases, or a few cases to check. It's really not that difficult. And in fact, the only cases you get are A is 1, B is 4, and A is 5, B is 5. I thought it would just be 16 over 2, but then I realized you'd also probably have to add 4 cases onto that where A equals B. I've probably done the maths wrong there, ironically. Anyway, you only have 3 solutions here. A, B is 1, 4, 4, 1, and 5, 5.